In this video, I'm going to go over Hooke's law. Hooke's law in Hooke's law, we're basically looking at a spring that's stretched, and it relates the restoring force of a spring when it's stretched from equilibrium. So the example for explaining this, right, is assume that we have a wall attached to a frictionless surface. And basically I have a spring attached to one side of the wall and a mass on the other side. Assume that this mass reaches equilibrium. The point is that if I pull the mass, the spring will pull it back, and so this mass will start oscillating back and forth. But let's assume that the position of this mass is at equilibrium, and this equilibrium point is my origin of my coordinate system. So here's my coordinate system, and I'll assume that x is positive going to the right hand side. And basically Hooke's law says that if I should pull the mass by a certain amount, or the spring itself, if the point of connection is attached to the mass, if I pull and stretch the spring by a certain amount by x, then the restoring force of the spring is given by a constant that is intrinsic to the spring times x, the displacement from equilibrium. So this is the spring constant. And this quantity is called the displacement from equilibrium. So let me give you an example of this. A spring has a spring constant of k is equal to 20 newtons per meter. And find the restoring force when the spring is stretched by 2 meters. Actually, let's put 2.0 so I can use two significant digits, 2.0 meters. So the idea is that we have the force from the spring, this is Hooke's law, is equal to minus a constant, the spring constant, times x. In this case, it's minus 20 newtons per meter, and x is 2.0 meters. The meters drops, and we're left with 40 newtons. And do you notice there's a minus that I forgot? I'll put it in right now. Let me erase that and do that again. So that's equal to minus 40 newtons. So the idea is that if my displacement, right, is in positive direction for 2.0 meters, the restoring force is negative, pulling back in the opposite direction. You'll also notice that the displacement is negative, right? So if this happened to be a minus 2.0 meters, right, it's contracted, the spring is pushed in by 2.0 meters, then the negative and negative would cancel to get a positive 40 newtons, which means that if I squeeze the spring, then the restoring force is in the opposite direction. So this is actually Hooke's law. This is Hooke's law. Now let me give another example where we actually have a spring that's hanging off a ceiling. So let me erase this. So here's an example a spring, and I'll use the same spring constant, with spring constant of K equals 20 newtons per meter is attached to the ceiling. What, I should say how much does the spring stretch when a mass of 5 kilograms is attached to the spring. So the idea is that we have a ceiling. Here's our ceiling. We have a spring. Here it is. It has an equilibrium point, and I attach now a mass. Here's the mass. And this mass is going to, so this is our origin at equilibrium, and then it stretches to a new point where, so here's our mass, our spring is stretched. So let me erase that. Do it over here. So this mass causes the spring to stretch from equilibrium. And we'll call, actually, I'll use x to mean down. X is positive when x is down. Okay, so the question is find x, find the displacement or the stretching of the spring. So we're going to do a free body diagram for the mass at the bottom of the stretch. So here's our free body diagram. So if I look at the mass, there is a force by the spring. I'll label it as Fs. And then there's a force of gravity acting down. The sum of all forces, right, at equilibrium after the stretch, right, would be 0. So we're expecting sigma F is equal to 0, which is the force of the spring plus the force of gravity pulling down. And the force of the stretch, right, the force of the stretch is given by minus kx. And I have to be a little careful about the direction. Notice that I'm using positive as down, and the force of gravity, since it's already pointing down, right, would be mg. And so if we solve for x, we'll see that x is equal to mg over the spring constant. In this case, it happens to be 5 kilograms. And actually, I should be using it's 2 significant digits everywhere, so I'll say 5.0 kilograms. Gravitational acceleration, let's say, is 9.8 meters per second squared, and divisible by the spring constant, which is 20 newtons per meter. So we could plug this into a calculator, but we can approximate it. This is about 10, this is 50. 50 divided by 2 is 2.5. So approximately the stretch is 2.5 meters. Approximately. There's an error of 20% because of the 9.8. Actually, it's a 2% error. Anyway, so this is an example of Hooke's law, and